Hello, my name is Nicholas Perriman, and this is my test one for Discrete. So the problem that I had was actually two parts. So part one was how many moves does it take to transfer a double tower of Hanoi from one peg to another if disks of equal size are indistinguishable from each other. Part two, assuming that there are n different sizes of disks and exactly m sub k disks of size k, determine A, the minimum number of moves needed to transfer a tower when equal sized disks are considered to be indistinguishable. So the basic tower of Hanoi is just three rods that you stack disks on with a variable number of disks. So you have to move each of those disks from the left side tower to the right side tower, and you can only move one at a time, and you cannot put the larger disks on top of smaller disks. So the example on this page takes 7 moves. Now, the double tower is the same, except there's 2 of each size of disk. Now, the thing with the double tower is that it can be approached in the same way as the single standard tower, as long as the disks are indistinguishable, that is. Because if they're indistinguishable, then we can stack them in any order. So we can basically just move the two disks of the same size at the same time. And that's how we get the minimum number of moves to solve the tower. So as far as mathematically solving the tower, we need to start by manually solving it. And so we got those values, and then we started comparing them and looking for an equation that kind of connects them. And the equation that I came up with was T sub n equals 2 T sub n minus 1 plus 2. And this equation has a base case of T sub 0 equals 0. So that's just something that we have to make sure is maintained throughout the process. So with this equation, you can also just make sure as you keep going through manually, or just checking with what you've already done manually, that it is in fact matching up. And if you've done more of these kind of examples and different sizes of towers manually, then you might notice a pattern with how many moves it takes, because a lot of these numbers are pretty close to powers of 2. So we could set up a second equation where T sub n equals 2 to the n plus 1 minus 2. And that will again match up with the number of moves for each of these towers. So in order to prove that with induction, we need to make sure that our base case is still correct for our second equation. So we set n equal to 0 for the second equation, which means that T sub 0 equals 2 to the 1 minus 2, or 2 minus 2, which equals 0. And after confirming that, we can assume that T sub k equals 2 to the k plus 1 minus 2. But our goal is to get T sub k plus 1 equal to 2 to the k plus 2 minus 2. So we start with the T sub k equals 2 T sub k minus 1 plus 2. We can add plus 1 to both of the sub k's. And so that'll make our left side what we're looking for. And our right side is getting on the way there because we can substitute in for the t sub k that's now on the right, and then we can distribute the 2 into that. So after distributing, our equation reads as t sub k plus 1 equals 2 to the k plus 2 minus 4 plus 2. And then once we add that 2 and simplify the equation, really, then we have our goal. And so we have proven this equation to be true. Now, the random tower, as I'm calling it, where each disk can have a different amount of disks, is definitely not as simple. While the disks are still indistinguishable, there isn't a pattern that applies to all disks, like no matter what. It's not just 2 of the previous plus 2. So, in order to try and solve the random tower, I did multiple manual workthroughs of the towers. So, the first one I did, the smaller disk, there were 3 of those, and the second disk, there was only 1 of those. And that took 7 moves to solve. So I set up an equation that did fit. And so that was 2 m sub 1 plus m sub 2 equals t. And in this case, t was 7. And the equation matched when you plugged in all of those values. This also worked for the second and third towers, which had moves of 5 and 7, respectively. The equation failed for the fourth tower when I added a third size of disk. And I think this is because I didn't have enough information to set up the equation, really. But after this point, I did have enough information. So when I plugged it in, I assumed that all of the smaller disks got summed together and multiplied by 2, but that got me the wrong answer. So then I had to look into it again. And the pattern that stuck out to me was, well, for that specific equation, 2 to the power of 2 times the m sub 1 plus 2 times m sub 2, and then plus m sub 3 equals t. And in this case, when I plugged in all of those values, I got a 9, which was the right answer. So I looked into generalizing that equation more, and I decided that n would be defined as like the largest disk size. So in this case, it was the third disk was the largest, therefore the n was 3. But it can't just be 2 to the n because I needed it to be 2 squared. So that's why it starts at 2 to the n minus 1 times m sub 1. And then it counts down from there until it would be 2 to the 0, or it's just 1. So we don't actually have to show that multiplying m sub n. So I didn't quite know how to mathematically verify this equation, but I did go through and verify my answer with standard towers, double towers, another random tower that I had put together and manually solved. So as far as I can tell, it does work. I just don't know how to mathematically solve it, which is where all of you come in, hopefully. Uh, while I wasn't able to solve it, maybe you can. And as far as I can tell, the equation that I wrote looks a lot like a Josephus problem. So I'm hoping that that might be the way to solve it, but I'm not certain. So I'd appreciate any feedback, and thank you for watching.